Hello, Dragons. Section 3.2 covers implicit differentiation. This is one of my favorite kinds of derivatives. I don't know why. I just like them. Okay? Okay. An explicit equation is one that is solved for a variable. An implicit is where the variables are embedded in the problem. Okay, so example of explicit would be y equals x cubed plus 16. And often an explicit equation is a function. So like, for example, here, f of t equals negative t squared minus 4t. Okay? But an implicit equation is something like this. The equation for a circle. And it doesn't always have to be that simple. They actually, in fact, are usually much more complicated than that. Okay, but an explicit equation is one where you can't easily solve for a variable, or it isn't worth solving for a variable. Okay, because sometimes it's just not worth the trouble because implicit differentiation is relatively simple. So here's how we go. Most of the time we're taking the derivative with respect to x. And everything we've done to this point, we've been taking the derivative of an x with respect to x. So if I take the derivative of x, I get 1 dx dx. But dx dx is just 1. I mean, it's not really a fraction, but it looks like a fraction, and dx dx is 1. So that's just going to be 1. But if I take that same derivative, but in terms of y with respect to x, now I'm going to get 1 dy dx. But I can't cancel that because it's dy dx, not dx dx. All right, same thing here. Derivative of x squared is going to be 2x dx dx, but we don't write the dx dx because it's just 1. But the derivative of y squared with respect to x is dy dx, and we do have to keep that. Same thing here. Derivative is going to be 5e to the 5x dx dx, which is just 5e to the 5x. But here we're going to have 5e to the 5y dy dx. So basically, every time you take the derivative of a y, you're going to write dy dx. Okay? All right, so let's look at this example. We have this function here. Oh, not necessarily a function. I use that word too liberally. All right, so step 1 is to take the derivative. So if I take the derivative of this, I'm going to do 2y. Took the derivative of a y. Have to write dy dx. Minus the derivative of 5x cubed. Well, that's just 15x squared. Dx dx, I don't have to write it. Equals the derivative of 3y is y. But I took the derivative of a dy or a y, so that leaves me a dy dx. Okay? Your second step is always to put all your terms with dy dx on the left side, everything else on the right. Okay? Now, let me explain this. You do not have to move them all to the left and all the non-dy dx's to the right. You can do the other way around, move all your dy dx's to the right and all your non-dy dx's to the left. But what's going to happen is your answer is going to be the exact negative of my answer. And if I'm using an automatic grader, it's going to mark it wrong and I'm going to have to go in and fix it. If I'm grading it by hand, I'm going to have to actually think a little bit about grading it. Don't make me think. Please move all your dy dx's to the left. Move everything else to the right. So I'm going to move this 3 over here, and I'm going to move this 15x squared over here. So that gives me 2y dy dx minus 3 dy dx equals 15x squared. And from there, it's very easy to factor out a dy dx. So easy, in fact, that in the previous step, you really could have factored out the dy dx here and just jumped to here. Okay, so in the future, if you feel that you can do that, it's okay. I just caution you, if you have a 1 in front of this, don't forget about it. Okay? All right, and your last step is to solve for dy dx. Well, you're going to do that because it's multiplied by this, which we'll call a coefficient. It's not really, but we're going to loosely call it a coefficient. So we're going to divide that away. So that gives me 15x squared over 2y minus 3. I cannot cancel my 15 and my 3 because it's addition and subtraction in the bottom here, okay? All right, you're going to follow these same steps for every type of problem. So I'm going to pause the video and you are going to try this one by yourselves. Okay, so pause your video right now and try this problem. It's a nice, easy one. All right, so we took our derivatives. Anytime there was a y involved, we wrote our dy dx. Then I moved my dy dx terms over to the left, my non-dy dx terms over to the right, factored out my dy dx, and divided by that coefficient. I cannot cancel those 2's because of the subtraction involved, and so there's my final answer. Okay? All right, there are 2 ways to solve problem number 2. So I'm going to show you how I would do it, and then I'm going to show you another way you might see it. Okay? So if I want to take the derivative of this, the derivative of sine is cosine, and then you're going to keep that xy. But then you have to take the derivative of that. Well, the derivative of that is first derivative second, but that's a derivative of a y, so you have a dy dx, plus the second times the derivative of the first, which is a 1. And then that's going to be equal to the derivative of 10x, which is just 10. But now this has to be distributed to both of these. So that gives me x cosine xy dy dx plus y cosine of xy equals 10. So then I have my dy dx times x cosine of xy equals 10 minus y cosine of xy. And then I can divide by this. So dy dx equals 10 minus y cosine of xy over x cosine of xy. Okay, now I could do some trig algebra here to simplify this, but most of the time you're probably going to be able to just leave your answer right there. Okay, but now let me show you another little tricky way to do this same problem. So when I take my derivative, just like before, I'm going to get cosine of xy, and then x dy dx plus y dx dx, we don't have to write it, equals 10. So then instead of distributing, this time I'm going to divide by this cosine of xy. Because that gives me x dy dx plus y equals 10 over cosine xy. Well, that's 10 secant xy. Just a different way of writing the same thing. So then I can subtract my y. Oh, I should keep that in parentheses. And then divide by my x. Okay, now technically I could take this, and because I have a single term in the denominator, I could break this up and make it 10 over x cosine xy, which would be 10 secant of xy over x. And then this would be minus y over x because they're going to cancel. So that would be minus y over x, which is going to be the same thing as this. Just a different way of writing the same thing. Okay? If you're doing it by hand for me, doesn't matter which way you do it. If you're doing it on the AP test, you probably want to be able to do it either way because then you'll know, you'll be able to look for alternative forms of the answer. Okay, alrighty, so find a derivative at a point using implicit differentiation. So first, I'm going to pause this, and you are going to find the derivative of this function implicitly. And then don't go any further, we'll work on the rest together. Alrighty, there's your derivative. You should have gotten negative x over y. Guess what? Every time you take the derivative of a circle, you're going to get negative x over y. I promise you. Always remember also that dy dx is the slope. Don't forget you found a derivative, so that's the slope. Okay, so now we want to find all of the tangent lines for this when x is equal to 1. Okay, so x is equal to 1 here, so that means we want to find this tangent line, and we want to find this tangent line. Okay, anytime where x is equal to 1. So if x is equal to 1, y is going to be plus or minus the square root of 3. So I'm going to have two tangent lines. I'm going to have one at 1 root 3. And I'm going to have another one at 1 negative root 3. So my slope for this one is going to be negative x over y. We're not talking unit circle really, so we don't have to rationalize that. So that'll be y minus y1 equals slope times x minus x1. And then for this one, my slope again, negative x over y, which is just 1 over root 3. So then my equation is going to be y minus negative root 3 equals slope x minus 1. Okay, there's your tangent lines. All right, a lot of times with implicit differentiation, they're going to ask you about horizontal and vertical tangent lines. Keep in mind, a horizontal tangent line exists when the slope is equal to 0, which means that your numerator is equal to 0. A vertical tangent line is going to exist when your slope is undefined, which means your denominator is equal to 0. Okay? So here we're going to find all horizontal tangent lines of this equation, and then we're going to find all vertical tangent lines of the same equation. So I'm going to find my derivative here, which is going to be 6x plus 4y dy dx equals 0. That's a huge mistake people make. When there's just a constant with an implicit problem, so many times they just write the constant, take its derivative, it's 0. So then dy dx is equal to negative 6x over 4y. I'll divide that by 2. It'll give me negative 3x over 2y. So there's my slope of the function. So it's going to have a horizontal tangent line when negative 3x equals 0, which is when x equals 0. Oh, but it's horizontal. It's horizontal. So if x equals 0, then that means that 3 times 0 squared plus 2y squared equals 16. That's gone. Y squared equals 8. So y equals plus or minus 2 root 2. So my tangent lines, my horizontal tangent lines are y equals 2 root 2. and y equals negative 2 root 2. Remember, they're horizontal. Horizontal tangent lines are y equals. Okay. Same thing, I want to find the vertical tangent lines. Well, that's when this derivative, the slope,